Today's topic is lifting properties of covering projections. Last time we introduced the concept of covering projection, checked some basic properties like a covering projection is a local homeomorphism. Therefore, its fibers are all discrete and it shares all the local properties of the base space and the top space are the same. That's what we have seen. Before proceeding with lifting properties, let me take up a few more properties and a bit of example and so on. Then come back to and go ahead with the lifting properties. Okay, so we had also established that local connectivity, local path connectivity plays a very important role in the study of covering spaces. So often all authors blanketly assume that the base space is locally path connected to do anything. But just to keep the theory on, we can assume, we don't have to assume that. Okay, if you want to do some serious thing, we may have to assume that. So the key was this theorem, namely, when you have locally path connected, then you can restrict the covering space to each path component of the top space, and yet it will be a covering projection. So you can study each of them separately and then put whatever observation you have made together. So this is why this theorem is very important. Okay, so this is what we have proved last time. Now, so this is what I will tell you. We shall assume that both base and total space of the covering projection are path connected and connected unless specified otherwise, or it's clear from the context. When you are discussing some examples, and that example itself is not locally path connected, then it's clear that it's not locally path, that's all. If we let something and then we are assuming this thing, this you have to make it, okay? This is what I am. Now, for example, this covering projection word is used by different people in a different way, slightly different way. So that is what one has to be careful, especially in algebraic geometry. A covering projection need not be the covering projection the way we understand it, but it is not too far. So I will give you an example. Look at the map C to C, Z going to Z power n. We have seen that Z equal to 0, okay, is a difficulty point. If you throw away that point, then this map C star to C star is a covering projection. On the point Z, there is only one point. On every other point, there are finite many points. So this kind of situation is acceptable to algebraic geometer. So he allows a number of points, some subset, some curve, some variety, on which the given map may not be covering projection. If you throw away that, then the rest of this will be a covering projection on a large open set. Okay, such things are called ramified coverings actually, because the point Z equal to 0 is a ramified point here, ramification point. So they talk about ramification points and so on, but their covering itself may have ramification. So they call it a covering projection. When they want to talk about the covering projection in our sense, then they say unramified covering. There is no ramification. So the more expressive thing, unramified covering, is used for covering projection, because covering projection for them is a larger thing which is more often used. That's the point. Okay. So this unramified covering projection is the word they use for the actual covering projection that we use. Okay, so here are a few exercises which are straightforward. You can try them, but I will not use them till you have mastered them. To take a covering projection, if X is Hausdorff, then X bar will be Hausdorff. It's the other way around here. You know that P from X bar to X is a covering projection, then it is a quotient map. So under quotient maps, if the top space X bar is Hausdorff, it does not imply that X is Hausdorff. That is the case here also. But suppose you have a finite to one covering projection, then X bar Hausdorff implies X is Hausdorff. If it's an infinite covering, then this is not quite true. Okay, so we will have an example for this one. But if finite, then you should show that X bar is Hausdorff implies X is Hausdorff. This is straightforward point set topological conclusion. Okay, so this example tells you it is R2 minus 0, 0. We have seen this example, and there is an action of the infinite cyclic group. The generator takes X comma Y to 1 by 2 comma twice Y. So more generally, the powers of the generator will take X comma Y to 1 by 2 power n X comma 2 power n Y. So these are all equivalence classes now. The quotient map is actually a covering projection. So this happens because we have already introduced the terminology that action could be even action. So this action happens to be even action. So this is a covering projection. Only thing is, just like in the case of C star to C star, Z1 to Z4, and here we have throw away the 0, 0. So 0 is a single class, so that creates problem. Okay. However, after you throw away 0, 0, it is a covering projection is all right. And this is Hausdorff is also all right because it is a space of Euclidean space. But look at the class of 1, 0 and 0, 1 in the quotient space X. These 2 points cannot be separated by disjoint open subsets of X. Okay, I think we have seen this one. If you haven't seen it yet, you should check this one again. Okay, so it is not Hausdorff. All right. So this example is in any case T1 space. Okay, so if it's a T1 space, if it's regular, it will be Hausdorff also. So it is not regular, neither normal, because normal plus T1 will imply T2. So it is neither regular nor normal. Okay, all these things are true in R2 minus 0 being a metric space, but the quotient, the bottom space fails to be satisfy all these separation properties. Okay, and here is an example. This also you can do yourself. But when I want to use it, I will prove this one. Okay, so take a covering projection. Take any continuous map. If you have S from X to X bar, okay, which is a right inverse to P, that means P composite S is identity, then you call S a section of P. If we have just this one, people also call it section, but then it won't be continuous. I want continuity because I am doing topology. That's all. So a section is a continuous right inverse. It may not be left inverse, right? So that is, otherwise then it would be, then P would be a homeomorphism. P is a surjective map. This is a left inverse. So there are lots of synthetic left inverses. Continuous inverses are difficult to combine. Now suppose you have a continuous right inverse, that's called a section. Let now X bar be connected, X be locally connected or locally path connected. So I am specifically saying these things here because for this exercise it's important, that's all. Now suppose that P is a local homeomorphism and X bar is Hausdorff. So I am not assuming it's a covering projection. The second part B, I am assuming P is a covering projection. No Hausdorffness. Okay? Either homeomorphism and Hausdorffness of X bar or just P is a covering projection. Then any section of P, like this S here, is automatically a homeomorphism onto X bar, which just means that it is now right inverse, left inverse also. It is a full inverse, so P becomes a homeomorphism. S is a homeomorphism, P is a homeomorphism. Okay, the hint is you show that Sx is both open and closed. Because X bar is connected, it must be the whole of X, whole of X bar. Okay, all right, now let us carry on with lifting properties. Homotopy lifting property, if you recall, okay, asserts that certain maps exist. What are they? Okay, what are they? Namely, if one map can be lifted out of a homotopy, then the whole homotopy can be lifted. That existence of a lift means P composite, whatever new map you get is the old map. So that is what we have seen, that homotopy lifting property. Okay, I am just recalling this. In mathematics, there is in a uniqueness, whenever you have uniqueness result, which goes hand in hand with existence result quite often. Like first order differential equation solutions. In a small neighborhood, they exist, and in a smaller neighborhood, it is unique. Such things are always nicer and much more applicable than just existence theorem. Okay, indeed, the uniqueness part actually helps to solve the existence part, proving the existence part. Okay, so this is the case here also. All right, so we shall first have this uniqueness result. Then we will use this uniqueness result to prove the existence of these lifts, homotopy liftings. Okay. So recall that if f from y to x, a map, and g from y to x bar is a lift of through P means what? P composite G is f. That is the meaning of lifts. Now we are always concentrating upon map x bar to x, and that is denoted by P. Okay. So here is a neat theorem. Take a covering projection now and a connected space y. Take a function f from y to x. Suppose by chance you have two lifts g1 and g2, okay, of y to x bar are two lifts of this f, and they agree at one point. Y belong to y, g1y equal to g2y. At one point they coincide. Then g1 is equal to g2. So this is exactly similar to the first order differential equation. If you specify the the initial condition, then it is unique. This is like initial condition. At one point, they agree. Then the whole thing agrees. Just like integration theory. Okay? Integrals are defined up to a constant, additive constant. Right? There is no addition, multiplication here. At one point they agree, continuity is there, that's all. They would agree. So the key is that Y is connected. That's all. Y is connected. Of course, P has to be a covering projection. Otherwise, for arbitrary spaces, this will not be true. All right? Arbitrary functions, it will not be true. So let us do this proof, which is very straightforward. Look at all points in Y at which G1 and G2 coincide. That is a subset of Y. It's given that this subset is non-empty. There is at least one point. Right? So, if we show that Z is open and closed in Y, then because of the connectivity of Y, it follows that Z is the entire Y. Z is equal to Y means G1 will be equal to G2 at all the points of Y. Therefore, what we want to prove now is that Z is both open and closed. So take a point Y inside. Let V be an evenly covered open neighborhood of Fy in X. Y is in Z, Fy will be in X, and X is covered, all points of X, whole thing is covered by, evenly covered by P. That's why P is a covering projection. So take a neighborhood which is evenly covered. And this neighborhood is neighborhood of Fy. Let U be an open set of X bar mapped homeomorphically onto V, because V is evenly covered. P inverse of V is a disjoint union of open sets. Each of them comes to V by a homeomorphism, namely under P restriction of P. Okay, so you choose one of them. Let U be an open subset of X bar mapped homeomorphically onto V by P. Look at G1 of Y, which is equal to G2 of Y. It must be in one of these open sets and choose that one to which it belongs to. Okay. Now choose W, an open subset of Y, in Y, such that G1 and G2 of this W goes inside U, because one point is going inside, then by continuity, this is open set, some neighborhood of that point must go there. Of course, I will make a different neighborhoods for G1 and G2, but then I can take the intersection of those two, W1 and W2. G1, W1 contains a U2, G2, W2 contains a U2, contains a U, okay, by continuity of G1 and G2. But now you take W equal to W1 intersection W2, you will get this one. Okay. Then look at PG1 of any Z equal to Fz equal to Pg2 of Z for every Z inside W, because Pg1 is equal to F equal to Pg2. Therefore, P restricted U is an injective mapping. It is a homeomorphism. P of this one equal to P of this two. Therefore, G1 must be equal to G2 for every Z inside W. By definition, this W is contained inside Z. By definition, W by choice, W is an open subset around the singleton point, whatever point you have taken Y. So what we have proved is Z is open. Okay. If X bar were Hausdorff, then the set of points wherein two functions, continuous functions agree, is automatically a closed set. But we don't want to do that. We can do without the assumption that X bar is Hausdorff. Okay, for proving that the set Z is closed. So take a point Z in Y such that G1 of Z is not equal to G2 of Z. We have to show that this is also open. See, this is the complement of capital Z. So I want to show that complement is also open now. So to show that, what do I do? Let V be an evenly covered open neighborhood of P composite G1, which is equal to P composite G2. G1Z is not equal to G2 of Z, but PG1 is equal to PG of 2, right? That is F. Is equal to F. It's always the case. Therefore, what is happening is this G1 and G2, G1Z and G2Z, they are in the same fiber. Call this as X. P inverse of X they belong to. Okay. So we can find open neighborhoods UI around this point and this point. Okay. On which P is a homeomorphism and such that intersection is empty. Because they are in different fibers. All that I have to do is I take this point G1Z, P of G1Z, X, and then take a evenly covered neighborhood of that. Look at the inverse image. G1 will be in one of them, G1Z, and G2Z will be in another one of them. Two of them are not, they are coming to the same point and they cannot be in the same open set above. So you get U1 and U2 which are not, which are disjoint. Okay. By continuity, now G1 and G2 are continuous function. You will find a neighborhood W of Z such that Gi of W is in the UI. Same thing again. You can take first different and then intersect. Okay. Oh, sorry, I should not use this cover. All right. It follows that W is an open neighborhood of Z, not intersecting Z at all because GUIs are disjoint. G1 of any point here will not be equal to G2 of the same point because they will be going to two disjoint open subsets here. So the entire W is in the complement of Z. Therefore, the complement of Z is open, hence Z is closed. Okay. So covering projection is the only thing which is used critically here. Okay. The next step is to prove homotopy lifting property of covering projections for singleton spaces. For a singleton space, what is the meaning of homotopy? We have seen it is a path. So this is called path lifting property. Okay, path lifting property for our covering projections. First we prove that one. First point wise we will prove, then we shall prove it for space wise. Take a covering projection. Okay, given a path from I to X, that's omega, and a point X bar in X upper bar, X capital X bar, such that P of X bar comes to omega 0. This is the starting point. It is like initial value condition. Okay, take a point above. Always points can be lifted, right? Because P is a surjective mapping. Okay, your starting point, you lift it up in X bar. Then there exists a path, say omega twiddle, from I to X bar, such that P composite omega bar is equal to omega, which is a lift. And the starting point of this omega bar is the point which you have chosen, X bar. Okay. We have already proved that such a thing will be unique if there is another path omega 1 with the same properties then agreeing at one point, then omega 1 will equal to omega at all points. But we don't know whether this exists. But the uniqueness of this will help to prove this one now. Okay? And it is not difficult. Let's go through this one. Similar proof like this one, we have used several times. Define Z to be all points inside I. Okay? Such that omega bar is defined up to 0 to t. Omega bar of 0 has to be this x bar that we have chosen. Then it is defined up to t means what? There is a function 0t to omega x bar such that p composite that is equal to omega. Observe that Z is a subinterval because if some point belongs to that, 0 to t will belong to that. Okay. So interval and contains 0. 0 is already there because x bar is there. Okay. 0 to 0 is just closed interval. Omega is defined already. Okay. Now take T naught with the least upper bound of Z. This exists because after all, this Z is a subset of the closed interval 0, 1, and so it's bounded above. Let's take this one's least upper bound, or what is called as the supremum. I want to show that T naught itself is in Z. First thing. Second thing, T naught is actually equal to 1. Essentially, this is similar to showing that 0, using that 0, 1 is actually an interval, namely it is connected. But we will hide it and make it easier. Just use the existence of supremum, and then you have that the supremum has to be inside Z, which is equivalent to showing that Z is closed. Okay? And T naught has to be whole of 1, equivalent to showing that Z is open. Okay. Start with an evenly covered neighborhood of omega T naught. Up to T naught, the map is defined. Okay, up to T naught. At T naught is a supremum. So if you take anything little smaller than T naught, the function is defined. Now I want to do it at T naught. So take a evenly covered neighborhood of omega T naught. Okay. For 0 less than epsilon less than 1, you put this notation. Namely, I am only interested in actually an open interval, but I don't know, one part may be closed and so on. So I will take a closed interval, no problem. Epsilon is positive, that is good enough, 0 less than 1. I epsilon is T naught minus epsilon, comma T naught plus epsilon. This interval may go out of I, right? It may be bigger than I and some part. So I don't want that. So intersect it with I. Okay. Now choose epsilon so that omega, this is notation. Now choose epsilon so that this omega of this I epsilon, which is a neighborhood of T naught, okay, that is contained inside V. V is an open subset containing omega T naught. So by continuity of omega, some neighborhood will be contained inside V. That's all. This condition is just omega is continuous. Now let Ui be an open neighborhood of omega bar of T naught minus epsilon by 2. Take T naught minus epsilon by 2, just T naught to the left of that. That point, up omega bar is already defined because T naught is supremum. So omega bar makes sense there. Okay. So take this one to be an open neighborhood of this one. That is mapped homeomorphically onto V. Okay, because V is evenly covered, this must belong to somewhere. Inverse image of V. Take that component of this U, that is my Ui here. Okay, Ui contains this point. Put lambda equal to now P inverse of omega. Okay, that is lift off. Is a lift off this becomes a lift of omega on I epsilon. See, this is the homeomorphism. P restricted to ui to v is a homeomorphism, so I can take P inverse there. Okay, P inverse is taken on this subset. Then compose it with omega. Omega composes P inverse. So this becomes a continuous function. If you take P of this, it will be omega. Therefore, this is a lift of omega inside the whole of I epsilon. Because this whole of I epsilon is contained inside V. Omega of that one is contained inside V. If I take omega of I epsilon, P inverse makes sense. Now, look at lambda of T naught minus epsilon by 2, okay, which is by definition omega of T naught minus epsilon by 2, okay. This is already there. Up to there, we have the path already. Therefore, by the uniqueness theorem, this lambda T must be equal to omega bar of T for every T inside this one. This omega bar is already defined. Now I have got a lambda. They both of them agree at one point. So in this whole interval, which is a connected subset, it will be what? It will be unique. So lambda T must be equal to omega bar. Therefore, omega bar can be extended from all the way from 0 to T naught plus epsilon. This must be plus epsilon by 2. That is a typo here. T naught plus epsilon by 2. Okay. So therefore, two lifts can be patched up. That means omega bar can be lifted up to 0 to T naught plus epsilon by intersection I. If this epsilon is still less than 1, then what you have shown is some point T naught plus epsilon is already inside Z. But T naught was supremum. Therefore, this T naught plus this epsilon intersection, this one is just 0 to T naught. So this just means that T naught is equal to 1 and T naught belongs to that simultaneously. T naught less than 1 will contradict the definition of T naught that it is supremum. So T naught must be 1. And once it is there, omega is defined up to there. So it's over. So let us stop here, and the true lifting property will be done next time. Thank you.